Thank you very much. Well, I'm thrilled to be here, and I hope this is not just a one-time event, but hopefully the beginning of a relationship between CUNY and Stern College, especially for the physics students and the physical science students. So in addition to being a research associate at the American Museum of Natural History, I'm actually an assistant professor at the College of Staten Island, which is a CUNY campus, and there's this really nice relationship between CUNY and AMNH that exists in not just astrophysics, a few other branches of science, but we like to think that it's strongest in astrophysics, really, and so we essentially have a lot to thank for Neil deGrasse Tyson, and we sometimes work with him, and as well as the physics doctoral faculty at CUNY, of which a lot of us are members. And so we can now accept students that are interested in doing astrophysics research at the CUNY Physics PhD program, keep you in the city, have you teach at different CUNY campuses, and we think there's a lot of potential for this program and really strengthening the astrophysics research that's going on in New York City. But today, instead of talking about my research, I'm going to talk about what's kind of a hobby of mine, but I think a really important one to share, which is exploring the contributions of women in astronomy. And so without further ado, why should we care about this? Why should we care about who is doing the astronomy? And I think it's really a question of overall equity and diversity in science, where if it's just, for example, white men doing science, we're really ignoring a lot of potential talent in the entire world. And so in order to do the best science we can, we want to pull from the largest pool of people, as long as we work on the, I think, very reasonable assumption that people across all walks of life have the potential to be talented in science. And so even in today's modern society, where women are outnumbering men in higher education, women are still not up to par in terms of earning those degrees in science. In certain scientific fields, women are better represented. For example, the biological sciences, women are more than 50% of the people that are earning degrees. But in especially the physical sciences and things like engineering, women are much less than 50%. And it gets worse as you go to higher and higher degrees and higher levels of employment, essentially. And we want to find out why. If it doesn't make a difference if a lot of girls are interested in math and or math or science in grade school, if they don't pursue it for careers and continue in the careers and assume the leadership positions in those fields. And part of the reason why women might be attracted to the biological sciences as opposed to the physical sciences is essentially, it boils down to stereotypes, where we think that in order to be feminine, we have to be nurturing. For some reason, the biological science are seen as a little bit more, I don't want to necessarily say soft, but they have to do with living organisms. It has, it's a little bit more kind of culturally appropriate for women to be biologists as opposed to chemists or engineers or physics or physicists. There's a lot of stuff that goes into that I won't really get into, but it's certainly detrimental to encouraging the broadest talent pool possible to contribute to the physical sciences. And it can often be very negative for a woman to be seen as masculine, and these physical sciences are seen as very, very masculine. It's also, if you don't even want to think about it in terms of these gender stereotypes, you can also think about it in terms of the lifestyles that we think are afforded by these careers. And so one thinks that to be a scientist, you might have to work 80 or 100 hours a week in a lab. You might have to give up your family. You might have to delay having children. You might have to be very, very competitive. You might not think that you can collaborate with other people or do a lot of the things that you might enjoy doing, but that's really not the case in science. I think science can be very collaborative. You can do a lot of writing. You can do a lot of communicating. You can do a lot of these things that women tend to be more attracted to in terms of searching for careers. What's also a little bit discouraging is that women historically have not been given credit for their contributions to science. And this is true for a lot of the people that I'm going to talk about, and some of the even more famous cases are slightly outside of astronomy. So Lisa Meitner worked on nuclear fission with some scientists in the early 1900s, and she was not really given the credit for the work as much as her male advisors were. And Rosalind Franklin famously probably would have been awarded the Nobel Prize for co-discovering DNA with Watson and Crick. It's a little bit of an open question because unfortunately she passed away before the Nobel Prize was awarded, and Nobel Prizes are not awarded posthumously, but She was close enough to being overlooked that it's still used as an example of the contributions of women not being recognized. And once we do start to recognize the contributions of the diverse population that contributes to science, we can help start to identify role models that will just increase the equity and diversity in science. And this doesn't just benefit the underrepresented minorities that are then encouraged to contribute to science, but it really does benefit everybody. Like I said, we can pull from a larger talent pool, and not everybody wants to work in a place where it's just kind of copies of themselves working together. I think hopefully modern people enjoy working in a diverse environment. And so this is the beginning of changing the culture that we live in. And I think an important way to do that is by looking at the past and acknowledging maybe mistakes that we have made and trying to rectify those. And one of the things that came out really recently is this Why So Few report from the American Association of University Women. And it addresses a lot of these issues in much more detail and much more rigorously by summarizing and citing various studies that have actually gone into why girls that even start out being interested in science, technology, math, engineering type things, why they start to be discouraged from pursuing them at a very, very early age. This way, okay. So as a brief outline of what I'll talk about 5 historical astronomical figures. I'll do this chronologically, and I'll include some of their biographical info where I think it's interesting. And then I'll talk about 5 currently active astrophysical researchers or astronomical researchers. And for them, I'll start not by age, but by their research area. So starting at the solar system and then going outwards through women that study the entire universe. And for these women, I haven't even included pictures of them for some reason. I made this choice when I made the talk, but what I really want to focus on is their scientific achievements and go through some of the kind of big ideas and what current astrophysical research is. And for all of these women, I'm going to focus very much so on their contributions to astronomy, because this is what we really want to recognize. Okay, so the woman that we consider kind of the very first female astronomer is Hypatia of Alexandria, who worked in Greece, or worked in Egypt, but under the kind of control of, I think I don't even know if it's the Greek or the Roman Empire, but that era of civilization, where we know people like Archimedes and a lot of male mathematicians, philosophers, astronomers that contributed to the body of knowledge that we have, but we don't always recognize the contributions of Hypatia. And so she was kind of a researcher, a student, as well as a teacher in mathematics, astronomy, and philosophy. And these at the time were, of course, all linked. Astronomy is essentially the oldest of the sciences, but it was really almost more of a study of mathematics and philosophy at the time, as opposed to real physics that was going on. Although they did have the skill to determine a lot of things that were essentially forgotten between now and then, like the curvature of the Earth, the overall size of the Earth, the distance between the Earth and the Moon, and things like that. So she was basically educated, or allowed to be educated really because of her father, who was also a scholar in Alexandria and a professor in Alexandria. And so it wasn't common at the time for women to be educated, but because of her father encouraged it, it was allowed. And she ended up editing the contemporary version of Ptolemy's Almagest. And so this is one of the more famous, longest lasting books in astronomy that discussed essentially the entire understanding of the universe at the time. And so the image on the left is an image from Ptolemy setting up the essentially celestial spheres that they thought was the structure of the universe at the time. And so she was really up to date on the most current understanding and the most current knowledge about the entire universe. She also contributed to mathematical work on conic sections, which is, of course, something that modern physics, mechanics, dynamics relies upon today, as well as orbital mechanics and things like that for astronomy. She was renowned as a skilled orator and teacher. So she was highly regarded, and possibly as highly regarded as a man would have been in that regard. And she also has a kind of a fascinating story as to her death, where she was brutally killed by Christian monks. And it's possibly this that leads to her kind of resurgence as a literary figure and a poetic figure. And maybe if it wasn't for this, we wouldn't really know about her contributions today. And so she's almost now more of a feminist icon as opposed to a kind of a scientific icon. But I firmly believe that we can use her as both. Okay, stepping up to be a little bit more modern, I'm going to talk about Caroline Herschel. And hopefully Herschel sounds a little bit familiar because she is the sister of perhaps her more famous brother and her more famous nephew. And her brother was William Herschel, who discovered Uranus, the planet Uranus. So together they were both born in Germany and moved to England, originally working as musicians, interestingly enough. And astronomy really was William's hobby, but that became his career. Because William was supported by the English monarchy, essentially, to build telescopes and to make these astronomical observations. And what they were essentially looking for was comets, as well as other objects that weren't comets. So this is around the time of the Messier catalog, and Charles Messier was a French astronomer, and they were essentially looking for comets, but there was a lot of kind of fuzzy objects in the sky that weren't comets. And so Charles Messier made a famous catalog of these not comet objects in order to remember the ones that he had found before and essentially look for the comets. And so William built the telescopes, and then Caroline helped a lot with the observations, in addition to doing calculations to figure out where exactly to look for these objects in the night sky. And so she was actually doing what we might think of as kind of the unladylike work of doing the actual calculations. And she even published a catalog of stars that improved and expanded on the work of the first Astronomer Royal of England. So this is the most prestigious astronomer at the time, who was a couple generations before Caroline, but she's essentially improving on his work. And so she was a fantastic astronomer in her own right. And she discovered 8 comets and 3 nebulae, which, this is the very beginning of telescopic observations, and the sky was just opening up, but this is a huge number for any accomplished observer. After William died, she returned to Germany to support her nephew John's work in astronomy. So it was a very astronomically inclined family, and Caroline for a long time was kind of working in the shadows of William and then John, but now she's recognized as having contributed a lot in her own right. So she was awarded several gold medals and honorary society memberships, which is very, very rare for women at the time. So she was recognized unusually for a woman at the time, but still kind of in the shadow of her brother and her nephew. And so I have drawings that she did of Halley's Comet, one of the most famous long-period comets in the solar system, and then the telescope that she used that was built by William but used extensively for her. And this was nice because this was before women were not allowed to do nighttime observations, which happened later in the 19th century, where women were actually not allowed to go to the telescopes up until surprisingly late, you might learn. Okay, so a little bit later than Caroline Herschel, and now in the United States, is Maria Mitchell. And Maria Mitchell is really famous in the Northeast for being one of the first female astronomers and even one of the first female astronomy professors. And so there's this is when women's colleges were starting to be opened. She was born in Nantucket to a Quaker family. And again, learned astronomy from her father. So luckily she had this kind of family influence and the family support of her education, and in fact her scientific education. She was working as a librarian and discovered a comet and was awarded a medal from the King of Denmark. So discovering comets even about 100 years after Caroline Herschel worked was still a very huge achievement. And so for somebody to discover a comet was internationally renowned, essentially. And again, she calculated astronomical positions for a government office. She did essentially very painstaking, very important work, and was essentially allowed to contribute in that way. She was the first astronomy professor at Vassar and directory of the college observatory there. So there's an image of her first class at the observatory. But she wasn't just a scientist. She was also a suffragist and abolitionist, and so she was very politically and socially active at the time. And again, she was at least a little bit recognized for her contributions to science by being elected to the AAAS, we call it, so the American Academy of Arts and Sciences and the American Association for the Advancement of Science, both of which are still around today and are still, I believe, male-dominated. But at least, women were recognized by these societies even a little over 100 years ago. And her original telescope is at the Smithsonian Museum of American History in Washington, D.C. And so I think the bottom image is from the internet, and so from a professional photographer, but the middle image is one that I think I took with my phone the last time I was there, because I was so impressed that it was there. It was really nice to see it. And, you know, for this to be recognized in the Smithsonian is kind of a huge thing. Okay, and I think Annie Jump Cannon is one of my favorites. And so with the next couple women, they are still really, they're contributing to modern astronomy. So discovering a comet, you know, working at a small observatory is not necessarily contributing to the overall kind of body of astrophysics. But Annie Jump Cannon was really one of the first astrophysicists. And so instead of just, you know, finding things, naming them, charting their positions, calculating their orbits and things like that, this is really the beginning of the spectral understanding of stars, which really leads us to understanding their physical properties, their chemical properties. So it's really the application of physics to stars, which in my mind is really solid astrophysics. So she was born in Delaware and learned astronomy from her mother and was allowed to be educated at Wellesley and Radcliffe colleges, so early women's colleges, where she could study physics and astronomy. But when it came to getting a job, there it became a little bit more difficult. So there was this thing at the time at the Harvard College Observatory, which is still one of the main places where astrophysics research is being done in the country. And Pickering, who was a professor of astronomy there, had computers working at his observatory or at his lab. And the computers were not machines like we know today. The computers were actually the women. And the name computer used to refer to the women that were actually doing the calculations. And so, of course, they were also referred to as Pickering's ladies and, you know, harem and stuff, terrible things like that, which, you know, hopefully don't happen anymore. But they were really doing the hardcore work. They were doing data reduction. They were doing photometry, which is measuring the brightness of objects. They were doing spectroscopy, which is what Annie Jump Cannon did. These were the women that were doing the real science. And so what Annie Jump Cannon developed is the modern stellar classification system. And if anybody's taken an intro astronomy class, you know OBAFGKM. That's essentially the astronomer's alphabet. And what it is it classifies stars in temperature, where O is the hottest stars and M is the coolest stars. And there's mnemonics to try to remember this, and I usually don't like to tell people it because the most common mnemonic I just want absolutely done away with. But for you guys, I'll tell you the original one, and then I'll tell you the new one. The original one is OBA fine girl and kiss me tonight. Kiss me, it stops at M. And then eventually in the college textbooks, they change it to OBA fine girl / guy, kiss me. Like, not enough. I think we should get rid of that. And so I say later tonight because there's actually 2 spectral types. Now there's 3 spectral types added for cooler and cooler objects, but that's a little bit besides the point. But so the OBAFGKM are for stars, and one of the ones that a student of mine came up with was Outback Australia for good kangaroo meat. And I like that because as far as I can tell, it doesn't have any kind of gender connotations in it or anything like that, although it is kind of making fun of Australia maybe. And so maybe we should find something a little bit more politically correct. But in any case, this is the beginning of understanding the physics of the stars, because it started out as actually an alphabetical classification. So A, B, C, D, E, F, G, K. I don't even know the rest of the alphabet anymore. But you know, it started with A, because A was the stars with the strongest hydrogen absorption lines. But Annie Jump Cannon, by classifying a huge number of stars, realized that just because a star had the strongest absorption lines in hydrogen didn't necessarily mean anything. It was an observational fact and not kind of a physical fact. And so what she realized is that the O stars were the hottest because instead of having hydrogen, all of the hydrogen in the atmospheres was ionized. And so there was absorption lines from ions instead of from neutral hydrogen. And then in the middle at the A and the F stars is where you have the strongest hydrogen lines because you have enough of the hydrogen in the neutral state that you have the really, really strong absorption lines. And as you get cooler and cooler, the hydrogen starts to form molecules, and so you again lose the strength of the hydrogen absorption lines because it's in molecules in these cooler and cooler objects. And so she really recognized the physics behind these objects. And the spectral classification. And she was essentially working by eye And the image on the left there is an example of a field of stellar spectra that she would work with. So it's essentially an image of a cluster of stars, but then it's spread out by a prism. So the light from each star is spread out by wavelength. And so that's why you see a smear like that. So it would essentially be a rainbow if it weren't a black and white image. But essentially she was observing the intensity, and you would see dark lines in the spread out spectra that corresponded to the absorption lines that she used to classify the objects. And she personally classified 250,000 stars. And this was published in the Henry Japer catalog, which we still use today in modern astrophysics. And this is just a huge contribution to astrophysics because, as you might guess, this is a really subjective thing at the time. It wasn't done by computers. It was done with photographic plates. And one person, different people could look at the same set of data and come to different conclusions. But because she classified everything herself, everything was very, very self-consistent, and so that much more valuable. And you might wonder who Henry Japer is, and he's the guy with the money. Actually, I think his wife ended up giving the money to Harvard College Observatory. But I find it a little bit ironic that the wealthy male donor whose wife gave the money to Harvard College Observatory, where a woman that was paid as little as a secretary did most of the work, and yet the catalog is named after the wealthy male benefactor. But she did eventually get recognized for her work. She was the very first woman to receive an honorary doctorate from Oxford less than 100 years ago. And so I want you to look at her timeline, 1863 to 1941. And she was recognized by an appointment to astronomers, so a faculty position essentially in 1938. 3 years before her death and after decades of working in astronomy. So these women, like I said, that worked in the Harvard College Observatory were essentially paid as little as secretaries and were treated effectively like secretaries, even though they were doing the real scientific work. And I think I have more information about it in this slide because Henrietta Swan Leavitt was also a computer at Harvard College Observatory. So she attended Oberlin and Radcliffe colleges, worked not at Pickering's lab, I think, but a little bit. Oh, she must have worked earlier because she died earlier, but I think she passed away younger, is what happened. But again, you know, her huge body of work contributed really to modern astrophysical research and modern astrophysical understanding. What Henrietta Swan Leavitt studied was photometry. So she looked at the brightnesses of stars. But her really, really important contribution was variable stars. And so she was measuring the brightness of stars over time. And essentially these were, you know, tiny little smudges that ended up looking dark on a photographic plate. And she would look at the same cluster of stars or close by galaxy of stars that were observed over a series of nights. And essentially her job was to see if any of those fuzzy little blobs changed in size, because that would mean a change in brightness. And so she discovered nearly 2,000 new variable stars. And even more important than finding new objects is that she determined a relationship between the period of the objects, so the amount of time it took them to change in brightness, with their luminosity. So their luminosity is kind of their intrinsic brightness. And in luminosity is something we can't generally measure unless we know the distance to something. And so what she did is for objects in clusters, star clusters and star-forming regions and things like that with known distances from Earth, she could measure their intrinsic luminosities. She could also measure their periods by seeing how quickly they changed in brightness with time. And she discovered that there's this period luminosity relationship that simply said that brighter stars, more intrinsically luminous stars, have longer periods. And this ended up being crucial for our understanding of essentially the entire universe. So this was then used to extrapolate to measure the distances to what at the time were called spiral nebulae. And spiral nebulae, we now know, are separate galaxies from our own, but at the time they just, you know, with small telescopes that were available at the time, they looked like fuzzy blobs that were similar to fuzzy blobs that we thought were in our own galaxy. And so it wasn't clear whether these were separate galaxies or just smaller nearby things in our own galaxies. And this relationship was used because it could be extrapolated to more distant stars, variable stars that were discovered in these spiral nebulae. Her relationship could be extrapolated to measure the distances to these spiral nebulae and proved that they were beyond our own galaxy. And the most famous proof of this was Edwin Hubble's law. And Edwin Hubble's law, so the period brightness relationship was used to measure the distance to these spiral nebulae. And then Hubble used measurements from another astronomer who was working at Lowell Observatory of the recessional velocities of these nearby spiral nebulae. And the recessional velocity is how quickly the objects appear to be moving away from us. And what Hubble famously found is that the more distant the spiral nebulae, the faster it's moving away from us. And this is essentially proof that the universe is expanding. And this was the fact that spiral nebulae were definitely outside of our own galaxy, as well as the expanding universe, are two cornerstones of our modern understanding of the universe. And so she also died relatively young and was mistakenly considered for a Nobel Prize from her work. But unfortunately, like I said, the Nobel Prize Committee has a strict rule of not awarding Nobel Prizes posthumously. But she was very, very close to winning a Nobel Prize if she hadn't passed away so young. Okay, so now I'm going to talk about modern astronomers. And so that my cutoff is kind of at the early 1900s. And for these women coming up, some of them I know a little bit more about than others, but I'm going to focus on their contributions to astronomy. And like I said, I'm not even going to show their pictures or anything like that. And I'm going to start within the solar system with Carolyn Porco. And Carolyn Porco is one of the primary investigators for the Cassini mission. And the Cassini mission is this amazing mission that's essentially the mission that keeps on giving. It was launched, I think, in 2004 possibly, and its original goal was to drop the Huygens probe through the atmosphere of Titan onto the surface. And it did that after just a couple passes, a couple orbits around Saturn, but luckily the lifetime of the mission has been extended again and again. So we've gotten these amazing images of Saturn, of its rings, of many, many moons around Saturn, and Carolyn Porco is essentially leading this imaging campaign to study all of these objects. And these are just two images. One's of Saturn's rings, and you can see there's a little kind of shepherding moon in there, where the moon is actually disturbing the rings and making these ripples behind it as it orbits through the rings. And then this is one of the more famous moons of Saturn called Enceladus. And you can see these kind of crazy ridges and things like that on Enceladus. And so Enceladus is thought to be a little bit geologically active. And Cassini's even observed kind of geysers going off that you can see when they're around the edge of Enceladus. And so she works at the Space Science Institute and the University of Colorado heading up this project, and hopefully for several more years to come as the mission is extended. Deborah Fisher is now working at Yale University. Up until a few years ago, she had been working in California, but now we have her on the East Coast. And she is one of the original contributors to the discovery of planets around other stars. And this is another kind of really, really huge change in our understanding of the universe effectively, where up until about 1992 or 1995, we thought that there should be planets around other stars based on our understanding of our own solar system and based on our understanding of star formation, but they hadn't been directly detected or even indirectly detected. And so it was still kind of an open question of how unique the planets in the solar system were. But finally in 1995, groups were able to find planets around other find planets on other stars using the Doppler shift technique. And so this is an indirect detection technique where you measure the radial velocity of a star, so the velocity of a star along our line of sight. And you can see in my little animations that if the star has a planet around it, it'll be kind of tugged in its radial velocity. And so even though we don't see the planet, we see the wobble induced by the gravitational tug of the planet on the star. So gravity essentially makes the planet orbit, but there's always an equal and opposite motion, and the star kind of wobbles around the center of motion of the system. So even if that center of motion of the system is within the star, you'll still see a slight change in the velocity of the star relative to the Earth's motion. And so what they measure is essentially the radial velocity of a star to very, very high precision over a period of time. And if they see a regularly repeating signal, they can infer the properties of the planet from that signal. And so this is another kind of animation that shows how the spectral lines shift. And so this is called the Doppler shift technique. And we might be more familiar of it, this technique with sound waves instead of with light waves, where if you hear an ambulance or a police siren or something moving towards you, the sound is compressed to a higher pitch, and then as it moves away from you, it's kind of spread out into a lower pitch. And the same thing happens with the light, where if the object is moving towards you, the wavelength that you observe is effectively shortened, and so you see it at kind of bluer ends of the spectrum. And if the object is moving away from you, the wavelength is effectively spread out, and so the line shifts to red parts of the spectrum. And so Deborah Fisher was part of the American group that first discovered planets around other stars. The very first detections were actually announced by a Swedish group. And the interesting thing was that we were looking for things like our own solar system. And so we were looking for fairly big planets fairly far out. So Jupiter is about 5 astronomical units from the sun, about 5 times as far away from the sun as the Earth is, and it's 1 Jupiter mass, we'll say. So it's about, I think it's about 1,000th the mass of the sun. The first planets around sun-like stars that they actually found were more than 1 Jupiter mass and in about 3 or 5 day orbits around their host star. And so these were called hot Jupiters. They were much, much closer to the host star than we ever would have expected just based on our own solar system. And so it really, it wasn't where they were looking for planets. And when they found them and essentially started looking at those short periods, the field kind of exploded, and it turned out there were a lot there. And now Deborah is currently working on her own, so she's kind of separated from the California group, is working at Yale University and is pioneering very, very high precision radio velocity measurements around lower mass stars. And with these, we might be able to find planets in the habitable zones around their stars, essentially. Because these are so planets where they're in the right position around their stars to have the correct temperature for liquid water, effectively. And around lower mass stars, they're going to be, those habitable zone planets are going to be closer into their stars, and so they're going to have a shorter orbital period. And so it'll be easier for us to find them, but because they need to be lower mass, the tug that they're going to induce is going to be very, very small. And so we have to have very, very high precision measurements in order to find these planets. And she's doing that with specially built instruments at the Cerro Tololo International Observatory, or Inter-American Observatory, I believe, in Chile. Okay, and another woman, so this is still stepping out, is studying the center of our galaxy. And I have a suspicion that if the Nobel Prize is awarded for the discovery of a supermassive black hole at the center of the galaxy, that's the if. Then if that happens, Andrea Ghez will definitely share this Nobel Prize. And so that's, you know, I said it first if it does end up happening. I borrowed it from a couple other people. But Andrea's work really proves that there has to be a supermassive black hole at the center of the galaxy. And a supermassive black hole is something that's millions of times the mass of the sun. And the way that she proved that there's a supermassive black hole there is essentially very, very complicated techniques, but very, very simple physics. It's effectively Kepler's laws. By using Kepler's laws to figure out, based on orbits of stars around a certain position, what mass has to be within those orbits. And so the left animation shows the technique, and the right animation effectively shows the results of her measurements. And so the left animation shows you adaptive optics. And what adaptive optics does is it corrects for the distortion in light induced by the Earth's atmosphere and really, really sharpens up the image that you can get. And the reason that we need to do this by looking, when we look at the galactic center, is that we're looking sideways through a very, very flat galaxy. And when we look towards the center of the galaxy as well, there's a lot more stars and gas and dust between us and the center of that galaxy. It's about 26,000 light years between us and the center of the galaxy. And this also requires looking at long infrared wavelengths, so longer than our eyes can see. You can see that I've labeled it, actually the Galactic Center group has labeled it 2.2 microns. And so that's much longer than our eyes can see, and these longer wavelengths can penetrate through the gas and the dust at the, between us and the center of the galaxy much, much more. So by using this adaptive optics technique, you can kind of sharpen each of the individual stars, and then what they do is take images of the stars over time. And so on the right here is the animation going from, I think, about 1995 up until 2010 of the observations that they've taken of these stars. And I want to, as this starts again, you can watch this yellow, the star with the yellow trail. is a star called SO2, and SO2 has actually had time to go all the way around the center of the galaxy. It's a slightly elliptical orbit, and so this star marks the very, very center of the galaxy where the location of the supermassive black hole should be. And SO2, because we've observed it go all the way around once, provides some of the best constraints for the mass of the object here. And basically the fact that we can measure the mass using Kepler's laws and constrain it to such a small radius at the center of the galaxy by using the positions of all these stars, it can't be anything else besides a supermassive black hole. And they've in fact measured both the distance to the center of the galaxy and the size, the mass of the supermassive black hole to very, very high precision. So it's something, like I said, something like about 26,000 light years, and I think they're closing in on about 4 million solar masses for the mass of the supermassive black hole. And there's a lot of details that I'm skimming over, and all of these individual stars essentially provide an independent measurement of that mass. And you might also recognize that this is, of course, a 2D image, and all these orbits are actually happening in 3 dimensions, and we don't necessarily get all of that information, so there's some inclination effects and things like that that we can't figure out, but by combining the measurements of all of the stars, we can place much better constraints on the mass. And so that's what she is working at, and so she wasn't my advisor, but I worked with some of her students on some other work. So I'm very proud to know that she's from my alma mater for my PhD. And then stepping out to other galaxies, Vera Rubin, who is at the Carnegie Institution of Washington, has helped prove that most of the matter in the universe is dark matter. So it's matter that we can't see effectively. It's non-baryonic matter. It's not made of the normal stuff that we are made of and that most of the particles that we can interact with are made of. And so what she did is she measured rotation curves for individual galaxies. So here's an image of a galaxy called M33, a relatively nearby galaxy. And as you go out in radius, this is a unit of distance called kiloparsecs. She measured the velocity of different things moving at different distances from the center of the galaxy. And again, using the shift in the wavelengths of light, you can measure the velocities of these things along our line of sight. And what you would the type of rotation you would expect from the light matter that you see there, which is effectively all we can see, is something like this, where it rotates faster because there's more and more mass. But then once you stop seeing light, you expect there to stop being mass, and you effectively expect kind of a Keplerian fall off where there is no more mass, and stuff further and further away should be orbiting more and more slowly. But that's not what she observed. She observed this increasing curve, and that essentially means that there has to be more mass than we can see. And this mass is, you can think of it as effectively bumping up this curve, because otherwise things would be going slower and slower and slower, and not faster and faster and faster as you got further and further away. And so this is one important piece of evidence that most of the matter that we can see is dark matter and doesn't interact with electromagnetic radiation, essentially. And this was essentially an advance on Fritz Zwicky's work, who also came to the same conclusion, but by studying clusters of galaxies instead of individual galaxies. Another woman who works at the observatories at the Carnegie Institution, so very similar but slightly different institutions. One's in DC and one's in Pasadena, California. I think they're actually the same institution, but slightly different kind of departments on the different coasts. And Wendy Friedman is studying the kind of even larger aspects of the universe. And so, like I mentioned, Hubble's law, where he measured the distances to galaxies and the apparent recessional velocities of those galaxies to show that the universe had to be expanding. Wendy Friedman led a project to measure the distances and the velocities to even more distant galaxies and show that essentially derive the expansion of the universe to higher and higher precision. And so these were the limitations of Hubble's measurements. And using the Hubble Space Telescope and other large, more modern telescopes, they were able to expand this out to much larger distances and place much better constraints on this number, 83, 75, and 67, are essentially the rate of expansion of the universe. So she was also using the galaxy, or the variable stars, but she was being able to measure them to more and more distant galaxies. Wendy Freeman was also the first woman to be the director of the observatories of the Carnegie Institution. And as the director, she's currently leading the project to build an amazing modern astrophysical observatory. So it's the Giant Magellan Telescope. And each of these mirrors is essentially as large as the current largest optical telescope. So each of these mirrors is about 8 meters in diameter. And they're essentially going to put together 7 of these mirrors to make one of the largest optical telescopes in the world. Okay, so that's the women that I wanted to present. Of course, there's many, many, many more than that. But these are some that have made nice kind of cornerstone contributions to modern astrophysical research. And despite the fact that science and even astronomy, even though there's more women in astronomy than there tends to be in physics and in engineering, women have made significant contributions to the physical sciences. And then I'm hoping by recognizing the contributions of women that we can effectively change the stereotypes of science and scientists, and this will help to make a more diverse and a more equitable community in scientific careers as well as in scientific education. And so here's a lot of, or at least a few resources that are probably too long to write down, but essentially Astro Society is the Astronomical Society of the Pacific, and they put together even more comprehensive biographies of women astronomers. And then the second one is the citation for the Association of American University Women study on why there's so few women in STEM careers. And then AWIS is the, oh man, now I can't remember. I think just Association of Women in Science, of which there is a local chapter. And there's even a lot of local women in science and engineering groups at different institutions. And I think even more than these kind of official groups, there's also kind of a grassroots movement that if you don't know about, I hope that you look into. One of them is a Tumblr that's called What Does a Scientist Look Like? And people just submit their photos, and they tend to be really, really far out there, which is nice. And it shows them with their families, and it shows people, you know, sometimes doing field work, but sometimes just doing their hobbies. And it's really, really nice to see scientists as people. And the huge variety of people that are already scientists or that are pursuing their education in science in order to have a research career. And it is more diverse already than I think society tends to think of us as, and we just want to make it more obvious that we are diverse, and hopefully that effect will kind of snowball and contribute to change the face of science. Thank you very much, and I'm happy to take some questions. No questions? Yeah.
Tell us a little bit about your research.
Oh, yeah. So I study brown dwarfs, which are kind of in between stars and planets. So I like to think of them as some people think of them as failed stars, because they essentially form like stars do from collapsing clouds of gas and dust, but they don't accumulate enough mass to start hydrogen fusion in their cores. So they don't create energy like the sun does or like other stars do, but they still, they have some energy left over from their collapse. And so they radiate a little bit, and they just kind of gradually cool and fade with time. But you could also consider them very successful planets. And in fact, that's kind of where our research is taking us, is that they cool and fade to have sizes and temperatures really similar to the gas giant planets that we're finding around other stars. But for the planets around other stars, they're really, really close to this bright thing. And so it's hard to get a lot of information about them. But the brown dwarfs are kind of out there in space. We know of quite a few of them fairly close by. And so we can take really, really detailed information of the brown dwarfs, try to understand their atmospheres. They have kind of not atmospheres like we would think of on Earth, where there's a solid surface, but their atmospheres, essentially their very outer layers, are much, much cooler than true stars, than stars like the sun or even the lowest mass stars. And so their atmospheres have clouds and have condensates and different layers and things like that. And their atmospheres are probably very similar to the atmospheres of giant planets around other stars. And we're hoping that with these detailed studies of the brown dwarfs, we'll effectively start to understand planets around other stars a little bit better as our observations of those objects get more and more kind of sophisticated. And so that's essentially what I do.
So I just have information of those stars, or
Mostly they're atmospheres. And so, yeah, and so we also do different types of measurements to try to constrain different properties. So I specifically measure their atmospheres, but because these objects cool and fade with time, we don't necessarily know how old they are. And so in order to...
What is the most interesting information would be how much mass, total mass is.
Yes, exactly. And we cannot...
How can you...
Yeah, we can't measure their masses unless they're in a binary system. And so there are people that study the binary systems in order to measure their orbits and directly measure the masses of the stars. But what we try to do is constrain atmosphere and evolutionary models that will essentially tell us the mass if we know, for example, the temperature and the radius and the luminosity or something like that. Yeah.
Estimates of how much mass is accumulated in brown dwarfs?
Yeah, so technically they're between 13 and 75 Jupiter masses, but that's just based on the nuclear physics.
In the universe.
Oh.
Percent of mass.
Oh, that's a good question.
Galaxy,
yeah. I don't know, actually. I don't know off the top of my head. It's not enough to be the dark matter. At first, when there was this missing matter seen in the galaxies and the cluster of galaxies, there's just not enough of them. The amount of matter that's missing is far too much. Oh, we have estimates of the number distribution. I just don't know them off the top of my head. So there's more of these brown dwarfs than there are more massive stars, but there's still not enough to make up the huge amount of mass that's missing. Because what's missing, based on what we can see, is something like 80%.
Does it follow from the theory of star formation? Or
in terms of the dynamics of a galaxy.
From observation of binaries and taking into account the statistics of binaries?
In terms of the dark matter in the galaxies. So in terms of the dynamics of the galaxies, you can figure out how much mass has to be there, and then you can infer how much mass there is from the luminous matter that we see. And so the brown dwarfs don't contribute to the luminous matter a lot, but there would have to be many, many more of them to make up all the missing mass that we need to explain the dynamics. And so there's still this dark matter that's a different type of particle than we know of. Yeah, I don't know the number density of brown dwarfs off the top of my head. There's a lot of them, but they're so low mass compared to the stars that it's not a huge contribution in mass. And we probably haven't found all the ones that are out there either. And there's a limit to how far away we can see them as well. I'd love to come back and give a talk on my research. And then I would have all the numbers. Yeah. Then I'll talk about more of the physics and stuff like that. Do you have a question?
Yeah. I mean, you mentioned before, I think it was Caroline Herschel, who was looking through the telescope. And then
yes.
you said that women were not allowed
yes.
outside at night anymore. Was that what kind of...
Yeah, and I don't know exactly what it was, but definitely it came to a point. I mean, the women at the Harvard College Observatory just a few decades later, they did not go to the telescope and take that data. Somebody had to go to the telescope and take that data, but it wasn't the women. The women were working during the daytime to analyze the data. And now it's kind of reversed, where the students go to the telescope, men or women, and the advisors tend to stay home and help the students analyze the data. And so I don't know a lot of that would be really interesting for somebody to figure out more of. What I do know anecdotally is that in the Palomar Observatory, which is one of these slightly older observatories, one of the biggest telescopes in the world for quite a few years in Southern California, the dormitory up there is called the monastery. Not because it was actually a monastery, but it was nicknamed that because it's where the husbands used to like to go to get away from their wives. And so there was no women up there up until, I want to say something terrible like the 70s or 80s or something like that. Yeah, where there weren't, women observers were not welcome at Palomar. Yeah, it's owned by the California Institute of Technology. And it would be interesting to find the exact details of that. I'm sure it wasn't an official thing, but it was definitely institutionally discouraged. And unfortunately, there's a lot of stories like that, and I think that's the thing, personally, that we have to deal with today, is this kind of not official but still very present bias against women. Yeah. I don't know how kind of political we want to get and stuff like that, but there's been a lot of research about unconscious bias or subconscious bias, and unfortunately women do it too, where, you know, if you see somebody that looks like a scientist, you assume they're a scientist. If you see somebody that maybe looks like a secretary, you assume they're a secretary. Even if you don't want to think that women can't be scientists and women have to be secretaries, that's, you know, it's hard to not act on these unconscious impulses. And we're at the point where, you know, nominally, politically, we're 100% equal, if that's even true. I mean, we're supposed to be under the law, but, you know, it becomes a little bit harder to fight the battle when it's 1,000 different tiny little things instead of one big thing, like not being allowed to vote or something like that. And so I think it's important that we don't kind of give up and say, okay, you know, now we can vote, we're fine. Or, you know, now we've had a female presidential candidate, so we're fine. You know, we're still underrepresented in Congress, we're still underrepresented at lots of different levels in academia and science, and so there's definitely lots of progress still to be made. That's a little bit of my soapbox. I try to keep it objective because I'm a scientist, but at the same time it's really hard to when you're passionate about it.
Is the field of astrobiology emerging?
Yes, definitely. NASA is a big sponsor of astrobiology. I just talked to a colleague over the weekend who went to a NASA astrobiology conference, and it's very, very interesting from what I can tell. It's really a combination of geology and chemistry and biology. It's not necessarily to find little green people, but it's about to understand the conditions that led to the development of life in a much, much broader context than we've ever thought of before. You know, and it's the exoplanets as well as the, you know, genetics and the, I don't even know what, you know, the proteins and things like that. So it's really all of the really cutting edge aspects of different fields of science coming together. And unfortunately, that's as much as I know, which is exactly how much I don't know. But definitely something to watch. Yeah.
Because it seems that with the growing population, in 5 years we'll have 10 billion people in this world.
Yeah.
It might be a nice idea to colonize.
Yeah, there's talk of what you would have to do to make Mars habitable. Definitely, that's actually a fairly realistic thing. You know, it wouldn't take that long to go to Mars, throw some more methane into the atmosphere, make a thicker atmosphere, warm it up, and boom, you've got Earth. There's a really nice exhibit at AMNH right now that's called Beyond Planet Earth, and so it's about, you know, moving to kind of civilizations on the moon, civilizations on Mars, and studying the asteroids, and you know, having human spaceflight to the asteroids. And it's long distances relatively in the solar system, but on the other hand, it's about to happen. Like, there's a private company that is they have a long-term plan and a lot of money to mine asteroids. So to get water out of them, to get precious metals out of them, like, you know, it might not be science fiction in the very, very near future.